Hi everyone, thank you for tuning into my talk. My name is Wei Tang. This is a joint work between Princeton and Oregon National Lab, also supported by the NSF Expedition EPIC project. This work is about combining classical and quantum computation to run large quantum circuits on small quantum computers. Quantum computing has emerged as a promising computational approach with the potential to benefit many scientific fields. Each additional qubit doubles the size of the computational state space available to a QC algorithm. Perhaps the most famous example is the Shor's integer factorization algorithm, which promises an exponential speedup over its classical counterparts. However, we're currently in the noisy intermediate scale quantum era, or NISQ, which are noisy and small. The figure here shows running the Bernstein-Vazirani, or BV algorithm, on IBM quantum devices at half capacity. For example, we're running 26 qubits on their largest 53-qubit Rochester device with 8,000 shots. The probability of getting the correct result, which is called fidelity, decreases to below 1% even on the 20-qubit Johannesburg device. The fidelity is effectively zero on the larger ones. Furthermore, the 53-qubit device is hard limited to run circuits smaller than 53 qubits. Even just one more qubit is currently impossible. The short story is, we want larger devices, but they're also much noisier. This shows that there's a huge gap between the quality and size of the quantum devices we have nowadays and the requirements of many proposed use cases for QC. The question is, how do we evaluate larger quantum circuits with better fidelity despite these challenges? Our approach, called CutQC, cuts a quantum circuit, then combines quantum processing and classical processing to run QC algorithms at larger scale. Essentially, we first cut large quantum circuits into smaller subcircuits that fit on small quantum computers. Use the quantum computers to evaluate small subcircuits. We eventually sew together the results using classical computing. The figure here shows an example of making one cut to split a 5-qubit circuit into two 3-qubit subcircuits. Instead of requiring a 5-qubit QC, we now only need a 3-qubit QC. Please refer to the paper for a detailed walkthrough on the classical reconstruction process. The challenge here is that classical reconstruction is time and resource intensive. We developed the first practical end-to-end circuit cutting toolchain. Our toolchain automatically finds optimal cutting points for large quantum circuits using mixed integer programming, uses small QC platforms to run the subcircuits incurred, and uses efficient classical reconstruction techniques to produce the uncut output in either full definition or dynamically adjusted definition. Our work beats classical simulation baseline in runtime and NISQ in fidelity and circuit sizes. Our first set of results run larger quantum circuits on 10, 15, 20, and 25 qubit devices. On average, CutQC achieves 60x to 8600x speedup over the classical simulation baseline. All of our circuits are larger than the quantum device backends, which means the small NISQ platforms could not have run these circuits at all. Our experiments show that densely connected circuits are harder to cut, larger quantum circuits generally require more classical post-processing, and having larger quantum computers generally improves the runtime but has a diminishing return. For example, the 5x7 supremacy circuit admits the same optimal cuts on either a 20 or a 25 qubit device. Our second set of results compares circuits run directly on the 20 qubit Johannesburg device without cutting and run in the CutQC mode on the 5 qubit Bogota device. We calculate the percentage of chi-square reduction, which measures how much noise CutQC reduces. Larger reduction is better. CutQC on average reduces 21% to 47% of the noise. As a result, small and reliable QC combined with CutQC is better than large but unreliable QC. To scale CutQC further, we developed dynamic definition algorithm to produce a blurred output for very large circuits. With this technique, we demonstrated running circuits of up to 100 qubits, well beyond the classical or quantum limit. Details of the algorithms are in the paper. Thank you everyone for listening to the short talk. Looking forward to seeing you at the live Q&A session.